So, how is it novel and different? And I think it'd be good to look at its own marketing pitch, basically, because if you consider Rust, it'd be good to see how they even market itself and they say what does it bring new to the table. So I'm just quickly going to the archived version of official rust-lang.org from May 2015, 15th of May, which was the day of the 1.0 release. And here we can quickly see at a glance how the syntax looks like. So imagine a mixture between C and C++, but with inspirations from ML and OCaml family of languages. But first, what's striking is this kind of, maybe not bold text, but big text that Rust is a systems programming language that runs blazingly fast, prevents nearly all seg faults, and guarantees thread safety. And this is interesting because this is the, I'd say, first mainstream language that, as a systems programming language, fairly low level, that prevents nearly all seg faults and guarantees thread safety. And by seg faults, this is segmentation faults, so any fault related to memory, so to speak. So what they say is basically that Rust is memory safe. And this is interesting because other languages provide that guarantee by using a garbage collector, but garbage collector also incurs a certain runtime overhead. When you create objects, all of them need to be analyzed by a garbage collector at a certain point of time, where, for example, most of the garbage collectors these days are mark and sweep stop of the world type. And what this means is that when you run your code, let's say, a couple of lines these languages need to stop, and the garbage collector needs to kick in and analyze all the data that is unused, and then clear it out, and then resume the program. But Rust wasn't designed with that in mind. Rust was designed in mind with full control in mind. And so it does not give you that, but still it retains the same guarantees, so to speak, as garbage collector languages, minus some minor issues, but I'm not going to mention these now because we don't have enough time. So let's go quickly through some of this, and maybe you'll better see how it achieves all that. So I have a nifty playground handy. This is a very cool site if you decide to toy with Rust in general, which is play.rust-lang.org. And it has few knobs and tweaks you can use, different channels, different optimization levels, and so on and so forth. So you can run interactively code yourself right now. And so I'll show you a quick example of, let's say, move semantics. And what move semantics is that we have certain values in the programming language, and these can be moved out, and when they're moved, they're invalidated. So imagine a very staple example, sort of practical, when you have a request builder, HTTP request builder. So this is a bit more advanced than the simple hello world, but please bear with me. I'm not going to explain the entire syntax, but I hope it's somewhat easy to understand. So what we want to do, what we want to achieve is to create a request. At this site, we want to set different headers. We want to inspect them probably. So we just collect into a big array and just display them using debug macro. And then we want to send them and see the response. But now, sometimes in dynamical languages, you're not aware of the state that certain values are. So for instance, in, let's say, Node.js, when you create a request, when you pass the handle of this request, this type, somewhere else in different functions, you may not know that it was already sent. And so mutating that and setting additional headers would be moot. You wouldn't get anything of it, and that would probably be a faulty behavior. So what Rust does is, after you send it, you need to annotate a function that consumes it. So you have three functions, set header, which accepts a mutable reference, a header, which is just a plain regular reference, and send, which consumes the value. And when the value is consumed, you can't do anything with it. So by calling send on request, this value, this is moved out of. So we cannot do anything with it. And we can see that when we try to run this code, this will effectively fail due to what we call a borrow check error in Rust. So when value was borrowed, it was moved out of, you basically can't do anything with this. And this prevents a whole class of errors that you can have. So if we can see that if we comment this line and try to run this again, it's going to take some time, and then we can see that this compiles and executes. And this doesn't work because this is executed in a sandbox, so we don't have a network access information. But if you do the same code on your local machine, you're going to get a normal, regular return data. Okay, so with this in mind, let's go to memory safety. Very brief, like I said, I don't intend to make this learn your Rust in 10 seconds or 10 minutes, but very briefly go through the main striking kind of pros and good points for it. So I have another example. So imagine you want to allocate stuff. And in languages like C, let's go maybe through this. So we have A, we create a vector of zeros repeated to 1024 times. So in JavaScript, this would be something like this. But this is a garbage collector language, so it would be collected as well when the A is out of scope. So what C++ brought to the table is a pattern called destructor, or RAII, which is resource acquisition is initialization. And so we can associate some resources with our structures. So vector is of type std of vec, but we don't have to explicitly type that. We could, but we don't have to because Rust has type inference. So it removes a lot of boilerplate that you don't need to repeat yourself all the time. So you have binding A, which creates a vector, but at the end of the scope, Rust compiler injects a certain function call to A, which just consumes the value and runs the destructor. And the destructor is just a normal trait, which is sort of like interface. And this is already implemented in Rust standard library, so we don't need to write anything ourselves. But this is kind of, it can execute some of the more complex logic at the end to manage our resources. But also we can go even deeper, and in safe Rust, it's not possible to, let's say, have a double free situation because it statically analyzes which value is uniquely referenced or multiply referenced. So as we saw in this example, there are three types of references, so to speak: a regular value, which consumes the value, a read-only value, and a mutable value, mutable reference to a value. So Rust statically analyzes your program and sees if you can execute the code and if you really have a single unique reference to a given value. And this allows us to eliminate these kinds of problems where we just pass on different references to different functions, like let's say in C or C++, just let's say we have a function that accepts reference of a given type like this. When we execute, let's say my struct, right? We just define a simple structure here. And it's not possible to have an instance that you can call with one mutable reference and then, let's say, spawn a thread that we can call another function with another mutable reference. This is not allowed. So this kind of static analysis eliminates whole class of errors, where in C++ you just pass a pointer to a different thread and you wouldn't know the difference. You could encounter a double use, double free, or use after free situation. But actually, speaking of threads, Rust also gives us another thing, which is, I need to bring back my archive. So what it also gives us is the slogan that they coined, which is a fearless concurrency. So in this case, this is just thread safety. And it does that by analyzing that using its own trait system and the language. So we have two traits, send and sync, and any type that implements send can be safely sent across different threads, and sync is a type, when the type implements trait sync, it can be safely shared across different threads. So for instance, I'll show these on example with a smart pointer, normally reference counted pointer, an atomically reference count pointer, and a mutex. And we also have refsol type, which is kind of the dynamically borrowed type. It maintains internally a counter of read-only borrows, and if you try to borrow it for read and no one mutably borrows it in the meantime, you're safe to go. But if any invariant that Rust guarantees does not uphold dynamically, then it just panics and just crashes your program. So either it crashes or it's safe to do. It doesn't give you like these silent corruptions of the state or any of that. In this example, we have a very simple structure which contains nothing. This is just a unit which can be printed using debug treats. And then we have the value that's wrapped by default in an atomically referenced pointer, ref counted pointer, that internally holds a mutex, which guarantees a mutually exclusive access to a value across different threads, which contains the value itself. But now this is the safe default, but Rust also has shadowed bindings. So let's analyze this case. This introduced arc of mutex of my struct, but this finally we only deal with just plain atomically referenced count pointer to a structure. And so this is safe to do. We can just clone different values. This is like a copy, and then we spawn different threads. We just print the value. And at the end, these are handles to threads. We just join them, wait, and we're finished, right? We can execute that. This is very simple. We just spawned two threads that debugged, that printed the instance of our structure. Now, there's no way to mutate that safely because we can safely share the value, but we have no guarantees. Arc as a type does not provide us with any means of mutating the value because we cannot guarantee anything about it. Like we cannot guarantee mutually exclusive access, unique access. So one can think if refcell allows us to sidestep that information and kind of dynamically give us the mutually exclusive access, then we can just use that, wrap that into Arc, and be good to go. And do, let's say, a and get mute, right? Which should be a function that tries to dynamically get a mutable value if no one else reads it. And the problem is refcell internally keeps a counter, but that counter is not thread safe. So this would introduce a bug in our program where we do not maintain those counters in a thread safe way and just corrupt our logic silently again. And now this is important because the Rust trait system allows us to give us that thread safety that you don't need to be an expert in writing concurrent and multi-threaded programs. It just gives you safety out of box. So for instance, this will not compile because the type arc, we can see the sync is not implemented for that. So this cannot be shared between threads safely, refcell, specifically refcell. And this is another point. Rust compiler diagnostics and errors are really maybe not verbose, but they give you a lot of information and they try to help you make better code. So it's not just a very not helpful error like types not implemented somewhere and you don't have any extra information. You have specifically this type of this cannot be shared at this point. You know, it's very helpful. It's like a pair programming, to be honest, Rust compiler. So it's also very good. So this is not thread safe. Arc is not because the inner type is not. But if we try to do the same as we had, but only share the data using not atomically referenced pointer, smart pointer, which is also a bug, we'll also get the error. So we had an error with sync. Now we have error with send. So RC itself cannot be even sent between threads safely because we don't have the atomicity that Arc gives us. So we just prevented another class of errors just by Rust being able to use its trace system to guarantee thread safety. And I think that's one of the biggest enablers that Rust gives you out of box, the safety and the freedom, but also the speed. So you don't need to be an expert like in C++, where even if you are, you're not, because the language constantly evolves and it has all the quirks that are very difficult to grasp. And I think the new kind of slogan fits what Rust gives very well. So what Rust really is a language that is empowering everyone to build reliable and efficient software. And I think that's the main takeaway, so to speak. But okay, enough about language. You can see the different bits, what makes it novel. And these ideas maybe are not novel, but languages that have them, that could provide thread safety or use borrow checking and have that mechanism of providing memory safety without runtime, they were very niche, they were very research heavy. And so people, if they knew about them, you couldn't really use them mainstream. And now Rust is taking world by the storm, and it's just a mainstream language that can compete with C and C++ in terms of speed and I'd say ease of development and teachability, very similar to some of the dynamic languages such as Python or even JavaScript.